Okay, so I'm recording. So let's start what we did yesterday. So yesterday we talked about the density of state, and we calculated the density of state for a metal for 3D, and the density of state is equal a constant, and then energy 1/2 to the power of 1/2. This is the density of state. It gives us how many energy states we have per electron volt. And then we also calculated for each those states, those are the states, energy states. If I take any one of them, depending on the energy value, what is the occupation probability? What is the occupation probability? Occupation probability for a given energy level. Energy level that has an energy E. And we say that there are two distributions. So actually there is a classical Boltzmann distribution that we are not covering here, but so the classical distribution of Boltzmann you have seen. This is the classical one. I'll just cover it. And the classical one is the probability of distribution or the probability of occupation of energy is a constant of energy level minus the energy divided by kT, but this has many pitfalls because of it does not really describe what the experimental measurement is given in most cases. So we have now a new one, which is the quantum mechanic based distribution, which is the Fermi Dirac distribution. This is what we started yesterday. So the Fermi Dirac distribution is the probability of occupation is 1 divided by exponential the energy minus the Fermi level divided by kT plus 1. Okay, this is the energy level, and we already mentioned that this is the energy in electron volt. EF is the Fermi level. I will explain what is the Fermi level. Again, it is the energy level, so it should be in electron volt, and K is the Boltzmann constant. And T is the temperature. Now, as I mentioned yesterday, the Boltzmann constant should be in electron volt per Kelvin, and Kelvin, let's do it Kelvin, and this one is in Kelvin also. The temperature is in Kelvin. Now, what we did, we started looking at the meaning of the distribution, and the first thing we did at T equals 0, and we have seen that if T equals 0, then the probability will have the following. The probability, the occupation probability for any energy that is smaller than the Fermi level, the probability will be equal to 1. And for any energy that is bigger than the Fermi level is 0. So this gives us a definition for the metal for the Fermi level. What is the Fermi level? If I look at the energy, and the Fermi level is the energy under which all energy states are occupied. So all energy states they have below the Fermi level, they have a full occupational probability, which is 1. So this is occupied, and this is empty. Okay, this is a T equals 0, and of course this is the outside of the metal. Okay, so the Fermi level is the energy under which, or below which, the energy level under which the occupation probability is 1, and after above this energy, the probability of occupation is 0. So there is no electrons. Okay, and this we look at it also from this plot that we described yesterday. The Fermi energy or the probability distribution, the probability of occupation as a function of energy. This is a Fermi level, and we have seen that this is 1, okay, and it is, so this is 1. So any energy that is less than Fermi energy value is less than, has a probability of 1. Now the Fermi level is a characteristics, is one of the characteristics of the metals. So for example, for lithium, the Fermi level of lithium is 4.72 electron volt. For copper, for example, its Fermi level is 0.4 electron volt, and so on. Okay. Now this is at t equal 0. You can hear me, right? You are following. Hello, can you hear me?
Yes, Professor.
Okay.
Yes, Professor.
Okay, so now what if t different than 0? Well, you can easily see that I mean, this you can do by calculation, but you can see that if I increase the temperature here, some of the electrons will have enough energy to jump. So which means the probability of occupation in this area, in the occupied area, will be less, or will start to decrease, and the one here start to increase. So this is at t equals 0. T equals 0, this is the probability of occupation, and this is the Fermi energy, and the energy. And now if I increase the temperature, let's say T1 different than 0, so what happens is that I start having this. So some of the states will start having, so those states that are here will start being populated, or the electrons that are here will start moving to the upper level. So we start seeing the energy levels that are beyond or above EF start being populated, because there are electrons that have enough energy to move to the upper levels. Okay. Yeah. So now, if I increase the temperature, let's say I have T2 bigger than T1, same thing happened, except that we have more and more energy states that are evacuated. Okay. This is T2. So you can see here we have more energy states that are evacuated from the below the Fermi energy, and more states that are populated after the below the Fermi energy. Okay. Now let's see what happens when T different than 0. What happens at an energy equal to EF? What happens at the Fermi level? Well, the Fermi, you can easily see that the probability of occupation of the Fermi level is equal to exponential of EF minus EF divided by KT plus 1. Since this is not 0, well, this one is 0, it gives you 1. And this means that the probability of occupation of the Fermi level is 1/2. And this is the value of 1/2. So whatever temperature is, if you increase temperature further, this will always go by the Fermi level, which is 1/2. So the probability of occupation of the Fermi level is 1/2. Okay, it's a very interesting characteristic. Any question?
Professor, can you repeat the last part?
Yeah,
Just
that was the last.
You could not hear me? Hello?
Yes, Professor, can you just repeat the last part? I didn't quite understand.
Okay. You mean from where? The Fermi level or everything from here? Let me see.
No, the Fermi level will increase the temperature.
Yeah, okay. So let also okay, I can repeat. Yeah. So when t is different than 0, is bigger than 0. So what happens is that what is the probability of occupation of the energy level that is equal to the Fermi level, right? So this means that all what I have to do is exponential of E. So I just replace E by EF. So EF minus EF divided by KT plus 1, right? Now, what is this? So this is EF minus EF divided by KT. This is 0 divided by KT. So I know that KT is not 0, okay? Because the temperature is not 0. So this quantity is equal to 0. And the exponential of 0 is 1. So this gives you 1/2. So the probability of a Fermi level, probability of occupation of Fermi level is 1/2. Okay. Now let's go to this curve. The energy, this is the probability of occupation, and this is the Fermi level. Okay, the Fermi level. And we have seen that at t equals 0, you have 1. So at t equals 0, you have 1. So this is at t equals 0, the black curve. This is 1/2. Now, whenever the temperature is different than 0, let's say I will call it T1, bigger than 0. So this T1, because the temperature is increasing, you get more state state are losing their electrons, and those electrons, they go to the upper level. So you have something like that. But you know that all energies will go through 1/2 at Fermi level. So all those, they will go. So this is T1. So you can see here, some of the energy levels are empty, and this is because some of the energy levels above the Fermi level are being occupied by those electrons that could get enough kinetic energy to move to the upper level. What I said also, if I have a temperature that is higher than T1, of course, both of them more than 0. So what happens is, because the temperature is higher, you have more and more energy states in the Fermi level that are being emptied, okay? And those electrons, they move to an upper level. So you have this thing. Okay? And obviously, if I go to another one, and so on. Okay? Is this clear? Were you able to follow?
Yes.
Okay.
Yes, Professor.
So this is what the Fermi level and the Fermi Dirac distribution is giving us. So now the Fermi level, there are two characteristics of the Fermi level. The Fermi level at temperature 0, all energy states that are below the Fermi level are fully occupied, because their probability of occupation is 1, and all the energy levels above the Fermi level are empty. This is one. The second characteristic, when the temperature is not 0, is above 0 degree Kelvin, then the Fermi, the probability of occupation of the Fermi level is 1/2. Okay, those are the two characteristics that you can, so you have to retain. Any question? Okay, so now let's see how can we calculate the Fermi level? Fermi level calculation. So the question is the following. If I ask you to calculate Fermi level of copper, for example, can we calculate it? We know that the Fermi level can be measured experimentally, but can we calculate the Fermi level analytically? And the answer is yes. Now, we know that at t equals 0, the Fermi distribution is equal to 1 below EF, of course, from 0 to EF. Okay, and is equal to 0 for the energy after F. Okay.
Mm.
Now here again, I will go to this energy level. This is the Fermi level, and let's assume I have a volume L cubed. This is a volume of my metal, and this is the number, the density. So Ne is the density of electrons, which means the density of electrons is the number of electrons per, so electrons per cubic meter. Okay. So what is the total number? The total number of electrons in this volume is just Ne times L cubed. Do you agree? No? Are you following?
Yes, yes, Professor.
So if I give you the density of electrons, which is the number of electrons per cubic meter, and I give you the volume, and I ask you to calculate the number, the total number of electrons, it's obvious the total number of electrons is Ne times L cubed. Now, we have seen that at t equals 0, all electrons are here. Well, this means that the integral from 0 to EF of the density of state, dE, must be equal to Ne L cubed, because the density, of course, Fe, sorry. No, wait, I need to, let me first explain something. Let me explain something. The first thing, I want to calculate the total number of electrons in this volume. I know that the total number is equal to the density times the volume. Now here I want to, before doing this, I want to specify two remarks. The first one, and this is a question for you, how to calculate the number of energy state, let's say, for example, between E1 and E2. Energy state, okay? Energy state. Any answer? Any idea? I want you to calculate, okay, if I take, let's say, this is energy 2, this is energy 1, and I wanted to calculate how many energy states are there, or energy levels are there between E1 and E2. We did it yesterday.
Integral, right?
Exactly. So the integral. So this number is given by the integral E1, E2, the density of state, dE. Please remember this. Okay. Those are typical exam questions. Second thing, how to calculate the number of electrons located or between in energy levels E1 and E2. Any idea?
Using the one you just gave us is equals to N times L.
Well, this is for the whole. I don't know what is the volume here. I don't know the volume. But I know that between E1 and E2, I have the number of states that can be given by the density, right? And I know that each state has a probability of occupation, the number of electrons, probability of occupation. All what I have to do is to integrate from E1 to E2 this quantity. So please remember this. This quantity is giving you the number, the green one that I just circled, is giving you the number of energy states between E1 and E2. This one is giving you the number of electrons populated between E1 and E2. Is this clear?
Yes, Professor.
Okay. So, and now we go back to our problem. So the problem was we wanted to calculate the Fermi level. And me also back. So we wanted to calculate the Fermi level. And we'll do it very quick because to repeat what I just said. So if I have, this is the Fermi level, and I know at t equals 0, all electrons are here, okay? And I know that the density of electrons is here, and L cubed is the volume. So the total number of electrons in volume L cubed is Ne L cubed, right? Do you agree? Okay. Now I can also calculate the total number using the density of state. I know from the integral of ZE FE dE, the total number of electrons must be equal to NL cubed. So this is, I know from just very classical calculations. But the quantum mechanics calculation is telling me that this also can give me the number of electrons. Now, I know that from at t equals 0, I'm doing this at t equals 0. At t equals 0, Fe is equal to 1 when E is less than EF, and is equal to 0 when E is bigger than EF. This means that this integral will just be the integral from 0 to EF of ZE dE, because E1, Fe is equal to 1. And this will be equal to Ne L cubed. Let's calculate this integral. Are you following? This is very important.
Yes, Professor.
Okay, so now let's calculate this integral. Well, we know that the density of state is equal to constant times 1. And this is, now it becomes very easy to integrate this. So the integral of 1/2 from 0 to EF dE is equal to, so what is the integral here? So it's 2/3 C, the integral of 3/2 from 0 to EF, okay? And this will give me 2/3 the quantity C, and then the Fermi level 3. Okay? This is the integral. But I know that this is equal to the number, the density of electrons times L cubed, right? So this means that the Fermi level 3/2 is equal to 3/2 the number of electrons, the volume, divided by the constant C. Any questions? Are you following? Hello? Then I can easily calculate EF by just isolating this. So this will just put everything to the power of 2/3. And this will give you the Fermi level is equal to h squared, Planck's constant, divided by 2 times the mass, and then 3 times the density of free electrons divided by 8 pi, everything to the power of 3. This is a very important thing. So what does this mean? Well, this means that we can calculate the Fermi level of any metal if we know the number or the density of free electrons. Okay, so if we know the density of free electrons, we can know we can calculate the Fermi level. Any question? Okay. Just give me 1 second. Can you ask him any idea how to calculate the Fermi level? Well, look, we just calculated a formula or derived a formula for the Fermi level that is 2m and 3 Ne over 8 pi to the power of 2/3. This is the Fermi level. So all what we have to do now is to calculate the number of the density of free electrons. So if you remember, we calculated this in the first chapter, right? But now I have I see that I have a good connection, so it's not a right. Okay. So can you how do we calculate, or how did we calculate the density of free electrons in the first chapter? We said it's equal to the density divided by the atomic mass.
times the Avogadro number.
Yeah, times the Avogadro number. Okay, so this is what we have to do. Of course, the density here. Well, the density we can because we have the atomic mass in gram. We can calculate. We can convert. So 20,000 times 10 to the power of 3 gram per cubic meters divided by 27, and then you multiply by 6, 10 to the power of 23, and then you get your this is cubic meter. You get the density in cubic meter. Okay, you get the density on cubic meter. Okay, cubic meter, and then the Fermi level will be the Planck's constant, 6.6 10 to the minus 34 squared divided by the mass of the electron, which is 9.1 10 to the minus 31, and then times 3 times the number of electrons, this is the one that we calculated here, and divided by 8 pi, and then to the power of 2/3. Now, I would like to give this as an exercise for tomorrow. Can you please calculate this? Calculate this value and compare it to the experimental value of the Fermi level of aluminum that is equal to 11.7 electron volt. Okay. Yeah, so well, what you can do the following, or let's give you 5 minutes to calculate it. If you have a calculator, let's calculate this value, and let's give me the exact number by chat. Let's take 4 minutes to do this. Can you hear me?
Yes, Professor.
Okay, let's do it. So you don't have a calculator in your phone? Huh. Okay, what about the others? So this will give you 602 10 to the power of 28 per cubic meters. Okay. Okay. And then, so what you have to do, so the reason I'm asking you to calculate this, because this is very important. It's a very easy calculation, but if you don't know how to do it in the calculator with a smart way, you will get, sometimes you will get 0 in your calculator, okay? And then, okay, so let's calculate it and give me the calculation later. I don't want to lose time. So let's continue. Okay, let's continue. No, that's too big. That's too big. Okay, so that's why I wanted to explain or to tell you. Now, the reason I'm asking you to calculate this, remember the Fermi level must be in electron volt. The Planck's constant is given in joule seconds. So you have to convert. So the Fermi level that you get here, if you do this basic calculation, the Fermi level will be in electron volt. Okay? And then now you got the same value, Arim and Umair. Let's divide this value or convert it to electron volt. So you get a value in joule. So the value that you get will be in joule because the Planck's constant here in joule. Now, if you divide this one by 1.610 to the minus 19, which value you get?
Wait, what do we divide with by that? 6.6?
Well, the value that you got, is in joule. The energy that you got is in joule. Now you
Oh,
want to convert it to electron volt. So you have to divide by 1.610 to the minus 19. Right? So if you do this, you get
5.57.
sorry?
I got 5.57.
Yeah. So 5.57. I'm not sure if let me look into the internet. What is the Fermi level of aluminum? Maybe no, Fermi. Yeah, no, it's 11.6. Maybe there is a mistake in the calculation, but anyway, it's a good yeah, it's a good. So I will give you the calculation later, but no, that's the good way to do it. So you do all the calculation and everything will be given in joule, and don't forget to convert it to electron volt. Yeah. Any question? So now let's also continue. One of the success of the quantum mechanics and the introduction of the density of states and Fermi-Dirac distribution is it could give us or help us in many in calculating the electrical and thermal properties of many of the metals, and also other, later we will see for semiconductors. As I mentioned, those are the three things. I will add another remark, but I will just summarize those remarks that I just did. So if I want to calculate the number of states of energy levels or states, so then I have to integrate ZED. Okay. If I want to calculate the number of electrons between two energy levels, So then I have to add the number of energy state and also times their occupation, their probability of occupation. Okay. Now, if I want to calculate the total energy, for example, I'm asking you, okay, what is the total energy of the system? The total energy. Total energy. Then the total energy will be the number of states times the probability of occupation and times the energy, and then dE. This is how you calculate the total energy. Those are very important quantity that you need to know. So let's talk about specific heat of solids. Specific heat of solids. So when the heat is applied to the metal, when we heat a metal, the free electrons absorb this heat. So these free electrons contribute to the specific heat of solids. Okay? So the classical theory of metals, classical theory of metals tells us that the energy, we have seen this, that the energy is equal to 3/2 RT. Okay. Now, what is the specific energy? So this is the total energy of the system. What is the specific heat? How do we define specific heat? Specific heat is just the derivative or the change, the rate of change of the energy. The rate of change of the energy. So this is the definition of the specific energy. Okay. Now, classical energy, the classical theory, it gives us that the energy of the system is 3/2 RT. This we got it from the classical Boltzmann distribution. If you remember, this is the first page of the discourse. Okay, so if we apply this, if we apply classical theory, the specific heat, which is the derivative with respect to T, to the temperature, sorry, is equal to 3/2, is a constant. Well, this is very interesting because the classical theory tells us that the specific heat does not change and it is constant as a function of the temperature, okay, because it's a constant. But this is in contradiction. It contradict experimental observation. So the classical theory does not give us an explanation of the experimental behavior of the specific heat. Okay? So now we want to go to the quantum description. So what is the quantum description? The quantum description tells us that the total energy of the system is the integral, is not this value, is not the one that we derived classically, but the integral from 0 to infinity, because we are integrating over the whole volume of the density of state, the probability of occupation of each state, and the energy. Okay, so this is the total energy. And then the specific heat will be just the derivative with respect to the temperature of this total energy. This is the density of state. Occupation probability and the energy. And then if we do this, it will give me the density of the specific heat, and then it is really proportional to the temperature. If we do the calculation, it will give you something proportional to the temperature. And this is, sorry, it's not, yeah, proportional to temperature. And this is in agreement with experimental value, with the experimental. As you can see, classical theory of Boltzmann tells us that the specific heat is constant. It does not change as a function of the temperature. But the classical description, the quantum description, tells us no. You have to integrate, you have to calculate the total energy using this description. And if you do this, you will see that it's proportional to the temperature, and it is in agreement with experimental values. Any questions? Okay, so give me 1 second. I will start giving a problem, for example, solving a problem. Let's say, now there's one question here. Yeah. Okay. There's one question here, for example, this one. What is the velocity of the electron at the Fermi level? No, sorry, the velocity of the electron at the Fermi level is this. Calculate its Fermi energy. Any idea? The velocity of the Fermi, we are given the velocity, okay? All what you have to do is to calculate the 1/2 mv squared. And 1/2 mv squared will give you the Fermi level. So what is 1/2 mv squared? Well, 1/2, 9.1, 10 to the minus 31. And then the velocity is 1/4, 10 to the power of 6. Okay. And this will be in, yeah, so I can give the calculation very quickly. Calculation very quickly. So it's 1.4 into the power of 6 squared multiplied by 9.131 and then divided by 2. And if I divide by 1.6 minus 19, it gives me 5.57 electron volt. Okay. And then the second question, I will copy it right now. Here. What is the density of free electrons for silver? What is the density of free electrons for silver? Any idea? How can you calculate the density of free electrons for silver? Hello, can you hear me?
Can we find the NE using the Fermi energy?
Exactly.
And
Yeah, exactly. So now, exactly. So we know
use
that the Fermi level is h squared over 2m 3n over 8 pi 2/3. What I want to calculate, I want to get this. Okay, so this means that 2m the Fermi energy over h squared 3 to the power of is equal to 3n 8 pi. This means the number of free electrons that I'm looking for is equal to 8 pi divided by 3 times 2m, the Fermi level, divided by h squared 3/2. Now, here we have to be very careful. I would do the following. This is the Fermi level. We already calculated the Fermi level. For me to be safe, convert this one to Joule because the Planck's constant in Joule, and this one is in kilogram, and that's it. And then you get the number of free electrons. Okay? Is this clear? Hello, can you hear me?
Yes,
Professor, so you want the number of free electrons in joules, not in.
No. The number of free electrons will be the number per cubic meters. No, what I meant is the following. Okay, so let me explain. So you have 2 times m EF divided by h squared. So this one, in the first question, we calculated it in electron volt. Okay, and this one is given in joule second, the Planck's constant. Well, this is an energy and this is an energy. Joule is an energy, the unit of energy. Electron volt is the unit of energy. So you have to use one of them. Either you have to convert h, the Planck's constant, to electron volt second, or you have to convert the Fermi level to Joule. I would prefer to convert the Fermi level to Joule, okay, and then do the calculation. And what you get, n is the number of electrons per cubic meters. So it's not an energy, right? Is this clear?
Yes.
Okay. But please do the calculation because, again, as I mentioned, some of the calculators, they are not able to calculate, for example, h squared. So please do the calculation and exercise because many times in the exam, I see a student asking me, my calculator is giving me 0. Well, you have to check first. Some of the calculators, they have a range that cannot calculate. For example, if you have h cubed, some of the calculators, h cubed is what? Is 6.6 cubed, then 10 to the minus 34 times 3. So some of the calculators, they cannot give you 10 to the minus 100. They stop at 10 to the minus 99. So they will give you 0 here, which is not true. It's not 0. So please pay attention or exercise yourself at home to do this kind of calculations with the calculator. Okay, so I will stop here and you can ask any questions. Yeah, just give me 1 second. Okay, so now I want to give an example here. Recording again. So what I was doing is the following, an example. So I was going to say start an example. So the example is